In this video, I'm going to take a look at November 2025, Paper 2, Grade 11, Physical Sciences. Question 1.1. The tendency of an atom to attract a bonded pair of electrons is known as electronegativity. Question 1.2. Which one of the following atomic combinations will have the shortest bond length? So, as the number of bonds increase, the bond length decreases. So the answer is going to be D. Question 1.3. Which one of the following substances has a tetrahedral shape? So tetrahedral shapes have essentially a central atom, and that's bonded to 1, 2, 3, and a fourth atom. So what we're looking for is something that has 1, 2, 3, 4, 5 atoms bonded together. So A, B, C is out. The answer is going to be D. Question 1.4. In which one of the following are ion dipole forces present? So we're looking for something that has ions in it and something that's going to interact with a dipole. Now NH3 gas is not going to be that. CO2 gas is not going to be that. LiCl aqueous solution. So let's look at that. So LiCl, Li plus and Cl minus. And in an aqueous solution means that there's water there. So a water molecule is going to appear like this. Now, here we are going to have an ion dipole, so the answer is going to be C, because the Li is going to be attracted to the negative oxygen, and the Cl will be attracted to the positive hydrogens. Moving on to question 1.5. 1 mole of a gas sealed in a container of volume V exerts pressure P. The volume of the container is decreased to 1 over 3 V, while the temperature remains constant. What is the pressure now exerted by the gas? So remember that pressure is going to be inversely proportional to volume when temperature is the same. So if the volume is a third, the pressure is going to be 3P. The answer here going to be B. Question 1.6. Consider the following statements about ideal gases. The gas particles occupy no volume. There are no intermolecular forces between the particles. The collisions between the particles are perfectly elastic. Which of the statements are true? The answer is D. All of them are true. Question 1.7. Which one of the following solutions will have the greatest concentration of H plus ions? So we're thinking about something that's acidic. So 2 moles of NH3. NH3 is a base, so that's not going to be it. 1.5 moles of CH3COOH. This is a weak acid, and so the concentration is not going to be 1.5. It will be less than that. We have C and D now. H2SO4, this is a strong acid. And HCl is also a strong acid. They have the same concentration. So what we need to look for is whether one is diprotic or not. H2SO4 is diprotic, meaning that when it dissociates, so you're going to have H2SO4 breaking into 2H plus SO4 2 minus. So if this is 1.5 moles per dm cubed, this is going to be 3 moles per dm cubed. So this is actually going to have a higher concentration compared to HCl, which is monoprotic. The answer is C. Question 1.8. Consider the following reaction. HNO3 plus X gives you NO3 minus plus HSO4 aqueous. In this reaction, X represents something. So HNO3 becomes NO3, which means that HNO3 acted as an acid because it donated a proton. Which means that whatever X is, it's got to be a base. So B is going to be out and D is going to be out. Now let's look at what the other compound is that formed. Well, HSO4 minus formed. So if that's the product, then it would have received a proton, meaning that before it would have been SO4 2 minus. So the answer here is going to be A. Question 1.9. The graph below shows the energy changes that take place during a chemical reaction. Which one of the following expressions corresponds to the activation energy of the reverse reaction? So activation energy is the activated complex and the reactants or products. So if we're looking at the reverse reaction, we're looking at the distance between these 2 points. So it's going to be Y minus Z. The answer D. Question 1.10. Consider the following redox reaction. So we have 10Cl minus plus 2MnO4 minus plus 16H plus, giving us 2Mn2 plus 8H2O and 5Cl2. The product of the reduction half reaction is, so product and reduction. So reduction is gain, so we're looking for something that gained electrons. So Cl minus went to Cl, that did not gain electrons. Let's look at here. So MnO4 minus, oxygen has an oxidation number of -2, so we have 4 of them, that's going to give us -8. That means the one Mn that's there must be +7. So Mn went from +7 to 2 plus. It gained 5 electrons, which means that Mn 2 plus is going to be the product of the reduction half reaction, because the reduction half reaction would be Mn 7 plus 5 electrons, giving us Mn 2 plus. Okay, let's look at question number 2. Consider the following reaction of nitric acid, HNO3, with lithium oxide. 2.1, define the term ionic bond. So an ionic bond is the force of attraction between oppositely charged ions that formed as a result of the transfer of electrons. Question 2.2, show that the bond between lithium and oxygen is ionic. So what we want to do here is calculate the difference in En. Now the difference in En is going to be 3.5 minus 1, which is 2.5. Now since it is greater than 2.1, so we'll say the delta En is greater than 2.1, therefore it is going to be ionic. Question 2.3, write down the name of the salt formed in this reaction. The name of the salt is the name of that compound, which is lithium and nitrate. Remember, the N is small letter n. Question 2.4.1. Consider the H2O molecule. Write down the valency of the O atom. Valency, number of bonds that the O atom can make, which is 2. Question 2.4.2, draw the Lewis structure for the H2O molecule. So we'll start with the O, since that's going to be my central atom. Oxygen is in group 6, so it's going to have 6 valence electrons. 1, 2, 3, 4, 5, 6. That means the 2 hydrogens must occupy this vacant spot here and that vacant spot there. So the hydrogen will go there and a hydrogen will go there. Question 2.4.3, what is the shape of the H2O molecule? It is bent, or you could say angular. Question 2.4.4, name the ion that is formed when H2O forms a dative covalent bond. So you're going to have H2O reacting with H+, and that's going to form H3O+. The name of this is the hydronium ion. Moving on, question 2.5. The above reaction takes place in a beaker. How will the temperature of the contents of the beaker be affected? Choose from increase, decrease, or remain the same, and then give a reason for the answer. So if this occurs in a beaker, the temperature of the beaker is going to increase. And that's because the delta H is less than 0, meaning the reaction is exothermic, which tells us that heat is given off. Moving on to question 2.6. 2.6 asks for the definition of bond length. Bond length is the average distance between the nuclei of 2 bonded atoms. Question 2.7. The diagram below shows the bonds that form between the atoms in the HNO3 molecule. Consider the bonds between the following atoms. Okay, so A is HO, B is NO, and C is N double bond O. 2.7.1, is the bond length larger in A or B? Explain the answer. It's going to be larger in B, and the reason is because nitrogen is a larger atom than hydrogen. And so the nuclear distance is going to be greater. Therefore, the bond length will increase. Question 2.7.2. Is the bond energy greater in B or C? Give a reason for the answer. It's going to be greater in C because C has a double bond. which means that there is a stronger force of attraction, which means that more energy is going to be required to break. So more energy to break. Let's take a look at question 3. The following table provides the bond energies between atoms. Consider the following reaction. CH4 plus 2O2 gives you CO2 plus 2H2O. Question 3.1. Define the term activation energy. Activation energy is the minimum energy that's required for a reaction to take place. Question 3.2.1. Determine the activation energy of the reaction. Now, for the reaction to occur, we need all of the reactants to break. So all the bonds in the reactants need to break in order for this reaction to occur. So in my reactants, I have CH4, which looks like this. And then I have two molecules of O2. So I have O, double bond O, O, double bond O. Now all of these bonds need to break in order for the reaction to occur. So I need to break 4 CH bonds and I need to break 2 OO bonds. So the CH has an energy of 413, so 4 into 413 plus 2 into 498, and that's equal to 2648 kilojoules per mole. So this is going to be the energy that's required for all of the bonds in my reactants to break. And this is going to be the energy that is absorbed. Now 3.2.2 says calculate the heat of the reaction. So to calculate the heat, the formula is delta H is equal to the energy that is absorbed minus the energy that is released. So to work out the energy that's released, we need to look at the products. Now in my products, I have CO2, so C double bond O, and I have 2 molecules of H2O. So H2O like this. Now the bonds that need to break, I'm going to have 2 C double bond O bonds, C double bond O that needs to break, and I'm going to have 4 OH bonds that's going to break. Now that's going to be 2 into C double bond O is 804 plus 4 into OH is 463. That's going to equal 3460 kilojoules per mole. And so this is going to be the energy that is released. Now I just substitute this into my formula above. The absorbed energy is 2648 minus the released energy is 3460, and that's going to equal minus 812 kilojoules per mole. This negative value tells us that the reaction is going to be exothermic, though they didn't ask for that. Question 3.3. How will the value calculated in 3.2.2 be affected if a suitable catalyst is used? Choose from increase, decrease, or remain the same, and give a reason for your answer. The answer is going to be remains the same. A catalyst does not affect the delta H of the reaction. So catalysts only change, or they only affect the activation energy, not the delta H of a reaction. Moving on, 3.4, 24 grams of CH4 reacts completely with excess O2 at STP. 3.4.1 asks, is there a net absorption or net release of energy? So there's going to be a net release of energy because this reaction is an exothermic reaction. So net release. Question 3.4.2, calculate the energy referred to in 3.4.1. So we have to be careful. We can't simply write that it's minus 812 because this is minus 812 kilojoules per mole. And so we've been given a certain amount of this. So we need to calculate the number of moles. So the number of moles here is going to equal the mass divided by the molar mass. So the mass is 24, the molar mass is 16. So 12 plus 4, which is 16. And that's going to give me 1.5 moles. So if minus 8 point, or if rather you can think of it as if 812 kilojoules is released per mole, then for 1.5 moles, you're going to have 1.5 multiplied by 812, which is equal 1218 kilojoules of energy that's going to be released. So going to be released for 1.5 moles. Moving on now to question 3.4.3. If 5.5 moles of gas is present when the reaction is complete, calculate the initial number of moles of O2 used in the reaction. Okay, so here I'm going to say CH4 plus O2, well 2O2, gives me CO2 plus 2H2O. All of these are gases. So they tell me now that 5.5 moles of gas is present when the reaction is complete. Now this is in excess. They tell us that this is excess, which means that this is going to be completely used up when the reaction is done. So at the end, when they are measuring and they tell us that 5.5 moles is present, it means that these three are going to add up to 5.5 moles because this is going to be used up. Okay? Now what we can do is work out what moles of CO2 would have been produced, what moles of H2O would have been produced, and what moles of O2 would have reacted, and then we can work out the initial. So if we had CH4 to CO2, and we calculated that we have 1.5 moles here, then from the ratio is 1 to 1. That means 1.5 moles of CO2 would have been produced. So if this is 1.5 moles, then we can do the same thing for H2O. So CH4 to H2O is a 1 to 2 ratio. So if this is 1.5, this will be double, so that's going to be 3 moles. So here we're going to have 3 moles. Then we can do CH4 to O2. Then this is a 1 to 2. So if that's 1.5, that's going to be 3 moles. So this is going to be 3 moles that reacted. Right? So from here, let's calculate. So I had 5.5 moles. Now the 5.5 moles were for this, and for this. So let's subtract. So minus the 3 moles for H2O minus the 1.5 moles for CO2, and that's going to give us 1 mole of O2 that was left over. Then we add it to the 3 moles that reacted. So 1 plus 3, so that's 4 moles of O2 initial. Question number 4 says, the graphs below shows the relationship between vapor pressure and temperature for CHCl3, CCl4 and H2O respectively. Atmospheric pressure is 101,3 kPa. Now we've been given this graph, vapor pressure versus temperature. It's important that we really understand what's going on here. The dotted line isn't put there for nothing. The dotted line is the line that essentially cuts off the 2 different phases. Because remember that boiling point is the temperature at which vapor pressure equals atmospheric pressure. So at this point right here, CH3 or rather CHCl3 will boil. At this point here, CCl4 will boil. At this point here, H2O will boil. That means anywhere below here, the substances are going to be liquids, and anything above, they are going to be gases. Now question 4.1 says, define the term vapor pressure. I've written it on the right. It is the pressure exerted by a vapor in equilibrium with its liquid in a closed system. Question 4.2.1, write down the vapor pressure of CCl4 at 70 degrees Celsius. So 70 degrees Celsius is here. All we need to do, bring it up till it touches the graph and then bring it across. The vapor pressure is going to be 80 kPa. Question 4.2.2, at what temperature that is the vapor pressure of CHCl3 100 kPa? So we're looking for 100 kPa. It touches the graph there, bring it down, and that's 60 degrees Celsius. So 60 degrees Celsius. 4.2.3, what phase is CHCl3 at 65 degrees Celsius? So 65 degrees Celsius is here, bring it up here, touches the graph of CHCl3 here, it is a gas. And then question 4.2.4, what is the boiling point of CCl4? So CCl4, we're looking for that intersection point right there. Bring it down all the way here, approximately 75 degrees Celsius. Now moving on to question 4.3, fully explain the difference in boiling point of CCl4 and H2O. So H2O has a higher boiling point, than CCl4. Now let's take a look at the intermolecular forces. H2O has hydrogen bonding and CCl4 has London. Now hydrogen bonds are stronger than London forces. That means more energy is going to be needed to break the bonds in H2O than CCl4. That's why H2O has a higher boiling point. Moving on to question 4.4, is CCl4 soluble in H2O? And then give a reason. So the answer is going to be no, it's not going to be soluble because CCl4 has London forces, as we said before. H2O has hydrogen bonds. They are not the same. Further, we can say that H2O is polar. CCl4 is non-polar. So like only dissolves like. So like dissolves like. So because they are different, one is non-polar and one is polar, one has hydrogen bonds, one has London forces, they're not the same, so H2O will not dissolve CCl4. Question number 5. An experiment was conducted to investigate the relationship between pressure and volume of a fixed mass of gas at temperature 273 Kelvin. The results obtained were shown in the graph below. We've got pressure and 1 over volume. Question 5.1. Name and state the law being investigated. So this is obviously going to be Boyle's law. And the reason because it's a fixed mass of gas and constant temperature. Now Boyle's law states that the pressure of an enclosed gas is going to be inversely proportional to the volume it occupies at constant temperature. Moving on, question 5.2. Calculate the volume of the gas when the pressure exerted by the gas is 101,3 kPa. So we're going to use the formula P1V1 equals P2V2. Now we want to know the volume when the pressure is 101,3. So P2 will be 101,3 and then V2 is what we want. Now P1V1 we get from the graph. So P1 is going to be 115,5. And then V, now we have to be careful here, it's not going to be 5,5 because on my x-axis I have 1 over V. So two things to note here. First, 5,5 times 10 to the power minus 3. So 5,5 times 10 to the power minus 3 is 1 over the volume. That means the volume is going to equal 181,82. So here we'll substitute 181,82 and now we can solve for V.
So V2 is going to equal 207,31 dm cubed. Moving on to question 5.3. Do real gases deviate from ideal gases at low pressures or high pressures? And explain the answer. So the deviation is going to occur at high pressures. And the explanation is going to be that at high pressures, remember the particles are going to be quite close together now. So they're going to be quite close. And so the volume of the molecules themselves are going to be more significant. Normally, we'll say that they are negligible, but when they are at high pressures, they're going to be quite close to one another. We cannot ignore it. So the reason here, so the volume of the gases is no longer negligible, meaning we cannot ignore it anymore. So then Boyle's law is essentially going to fail, because Boyle's law states that as you increase the pressure, the volume is going to decrease. So we can then say that increasing pressure no longer decreases volume, because remember Boyle's law states that pressure and volume are inversely proportional. So at this, or in this instance, it's not going to actually work. Question 5.4 states, draw a sketch graph of pressure, so y-axis, and volume, x-axis, for this experiment. No values or labels. So if P and 1 over V are directly proportional, it means that P and V are inversely proportional. So in inverse proportionality, it looks like that. Question 5.5. So they tell us the experiment is repeated using a greater mass of gas at 273 Kelvin. The results obtained are plotted on the same set of axes. Question 5.5. Which graph, A or B, will be obtained for the greater mass? Explain the answer. So that's going to be A. And the reason why it's going to be A is because that has a greater gradient. Now the ideal gas formula is PV is equal to nRT. Now PV is my gradient, and N is the number of moles. So the higher the gradient, the higher the number of moles. Let's take a look at question 6. 6.1, a 1.5 gram sample of a compound containing carbon, hydrogen, and oxygen was completely burned in air. The products formed were 1,74 grams of CO2 and 0,7 grams of water. Question 6.1.1 says, define the term empirical formula. Now, empirical formula, as we know, is the simplest whole number ratio of elements in a compound. Moving on to question 6.1.2, determine by calculation the empirical formula of the compound. Now I'm going to write out the reaction. So I'm going to say that CxHyOZ reacted with oxygen, so O2, to give me CO2 and H2O. Now this was 1,5 grams. Then the CO2 that formed was 1,74 grams, and the H2O was 0,70 grams. Now the reason why they've given us this is because they want us to know that the masses need to be the same on both sides. So what that means is the mass of the carbon on the right hand side must be the mass of the carbon on the left. The mass of the hydrogen on the right must be the mass of the hydrogen on the left. And then we can figure out the mass of oxygen. So let's figure out the mass of carbon. 12 divided by CO2 has a mass of 44 multiplied by 1,74. So essentially what we're doing is the composition, the percentage composition. And that's going to give us 0,475 grams of carbon. Now remember, that's going to be the mass of carbon here. So 0,475. Then we'll do the same thing for hydrogen. And that's equal to, there's two hydrogens here. So 2 divided by 18 multiplied by 0,7. And that's equal to 0,078 grams. So here, 0,078. That means the mass of oxygen is going to be the balance. So we'll say 1,5 minus 0,078 minus 0,475, which is equal to 0,947. Then we can calculate number of moles. So we'll say that the number of moles for carbon is going to equal the mass divided by the molar mass. The mass is 0,475. The molar mass of carbon is 12, and that's equal to 0,04. Then the number of moles of hydrogen is going to equal 0,078 divided by 1, which is equal to 0,078. The number of moles of oxygen is going to equal 0,947 divided by 16, and that's equal to 0,059. Now we can do a ratio. So carbon to hydrogen to oxygen. So 0,04 to 0,078 to 0,059. We'll divide everything by 0,04 because that's the smallest number. We'll get 1 to 2 to 1,5. Now we multiply everything out by 2 to get rid of the 1,5. We'll have 2 to 4 to 3. Therefore, our formula is going to be C2H4O3. Moving on, question 6.1.3. If the ratio of the empirical formula to molecular formula is 1 to 3, determine the molecular formula of the compound. All this means is that we take our empirical formula, multiply everything by 3 to get the molecular formula. So C2H4O3, and we're multiplying everything by 3. That's going to give us C6H12O9. Question 6.2, an iron ore, so impure sample, contains 30% of Fe2O3. Question 6.2.1 says, write down the oxidation number of iron in Fe2O3. So all we got to do here is switch the numbers. So the 2 goes up there and the 3 goes up there. So it's going to be 3 plus. Question 6.2.2, calculate the mass of iron that can be obtained from 150 grams of this ore. So we'll say that 30% of it is pure. So 30 over 100 multiplied by 150 grams. And that's equal to 45 grams. So 45 grams is pure Fe2O3. Now to calculate the amount of iron that we can get, we'll say that iron has a mass of 56. So 56 times 2, because there's 2 ions in there, divided by the mass of the whole thing is going to be 56 times 2 plus 3 times 16, because there's 3 oxygens. And then we're going to multiply this ratio by 45, and that's going to give us the mass of iron that we're going to get. And that's going to equal 31,5 grams. Let's move on. Question 6.3. In an experiment, a learner reacts 1,51 dm cubed of sulfuric acid, H2SO4, of concentration 0,43 moles per dm cubed with solid lithium. The balance equation for the reaction is. The graph below shows how the mass of lithium changes with time during the reaction. So we've got this reaction, and we can see that the reaction ends right here. And the mass of lithium at the end is 1,24 grams. Now this means that lithium is the excess reagent and H2SO4 is the limiting. Question 6.3.1, define the term limiting reagent. So the limiting reagent is the reactant that is used up completely in a reaction. Question 6.3.2, identify the limiting reagent in this reaction. Give a reason for the answer. So the answer is going to be H2SO4. And as I said before, that's going to be because there is 1,24 grams of lithium left over, which means that lithium is in excess. Moving on, question 6.3.3. Calculate the value of Y as shown on the graph. So essentially what they're asking is, how much of lithium did they start off with? So all we got to do here is understand that this 1,24 is the amount that's left over. And then the difference right here, from there to there, that's the amount used. So if we figure out the amount that was used and we add it to the amount that was left over, we're going to get the amount that we started with. So let's look at the information that we've got. They tell us that we have a volume of 1,51 dm cubed of sulfuric acid. We also know the concentration is 0,43. We can calculate number of moles. So number of moles is going to equal concentration times volume. 0,43 multiplied by 1,51. That's going to equal 0,65 moles of H2SO4. Now we can do a mole ratio to actually figure out the moles of lithium that was used. So from the reaction, the ratio of H2SO4 to lithium is 1 to 2. So if I had 0,65 moles here, then I'm going to have double that in lithium. So that's going to be 1,3 moles of lithium. Now I can convert this to a mass. So the mass is going to equal the number of moles times the molar mass. So 1,3 multiplied by 7, which is equal to 9,1 grams. And this is 9,1 grams of lithium that was used. So the difference from here to here is 9,1. So the initial is going to equal 1,24, so the amount that was left over, plus the 9,1, which is how much was used, and that's going to equal 10,34 grams. Let's take a look at question number 7. 7.1 reads, acetic acid ionizes in water according to the following balanced equation. 7.1.1, define an acid according to the Arrhenius theory. So according to the Arrhenius theory, an acid is a substance that produces hydrogen or hydronium ions when it dissolves in water. Question 7.1.2, write down the formula of two acids in this reaction. So obviously we're going to have CH3COOH. That means H2O is going to act as a base. Now H2O is going to form H3O plus. So this is going to be a conjugate acid. So my two acids are going to be CH3COOH and the other is going to be H3O plus. It's basically acid-base conjugate pairs. Question 7.1.3, is acetic acid a strong or weak acid? Give a reason for the answer. So acetic acid is a weak acid, and the reason why it is a weak acid is because it ionizes partially. So ionizes partially, and we can't forget the next part, to produce a low concentration of H3O plus ions. Moving on, question 7.2. A nitric acid solution has a concentration of 0,15 moles per dm cubed. In a reaction, 31,3 cm cubed of the HNO3 solution neutralizes 24.5 cm cubed of calcium hydroxide, according to the following balanced equation. Question 7.2.1, calculate the concentration of the calcium hydroxide solution. So this is a neutralization, and so we can use the formula CAVA divided by CBVB equals NA over NB. Now, the beauty of this equation is that we don't need to do any conversions. So the concentration of the acid is 0,15 multiplied by the volume of the acid. They tell us that it is 31,3 divided by the concentration of the base, which is what they want. The volume of the base that they used was 24,5, and that's equal to Na. So N is the ratio, so 2 over 1. And now we can solve for Cb. That's going to equal 0,1 moles dm to the power minus 3. 250 cm cubed of the nitric acid HNO3 solution with the same concentration of 0,15 moles per dm cubed is now reacted with pure zinc. The pH of the final solution is 2,174. Assume that the volume of the solution doesn't change. Question 7.2.2, calculate the mass of zinc that reacted. So I'm going to start by calculating the number of moles of HNO3. That's going to equal the concentration multiplied by the volume. The concentration was given as 0,15 and the volume is 0,25 dm cubed. 250 converted to dm cubed. That's equal to 0,0375 moles at the beginning. So we've got the initial amount, and that is 0,0375. Then the amount that was used for the reaction, and then if you subtract them, you'll get the amount that's left over. So the amount that's left over can be calculated by using the pH. So we can calculate the concentration. So pH is going to equal minus log the concentration of H3O plus. Now they've given us the pH of 2,174. That's equal to minus log concentration H3O plus. Now the concentration of H3O plus is therefore going to equal 10 to the power minus 2,174, which is equal to 6,7 times 10 to the minus 3. So this is the concentration of the H3O plus. Now because HNO3 is monoprotic, the concentration of HNO3 is going to equal the concentration of the H3O plus, which we now know is going to be 6,7 times 10 to the minus 3 moles per dm cubed. We can now convert this to number of moles because we know the volume. So the number of moles here is going to equal the concentration times the volume. The concentration, 6,7 times 10 to the minus 3, multiplied by the volume, which is 0,25, and that's equal to 1,675 times 10 to the minus 3 moles of HNO3 at the end. So this is the leftover amount, the 1,675 times 10 to the minus 3. So now if we want to figure out the amount that we used in the reaction, we simply need to subtract. So if I subtract these two, I'm going to get 0,0358 moles that was used in the reaction. Now that I know the moles used in the reaction, I can do a mole ratio. So the mole ratio between HNO3 and zinc is a 2:1 ratio. So if I've used 0,0358 here, then half of that will be zinc. So 0,018 moles will be zinc. We can calculate the mass of the zinc by saying number of moles times molar mass. Number of moles, 0,018 multiplied by the molar mass, 65, and that's equal to 1,16 grams of zinc. Moving on, question 7.2.3, calculate the volume that the hydrogen gas produced will occupy at 25 degrees Celsius. Take molar gas volume as 24,000 cm cubed per mole at 25 degrees Celsius. So 24,000 cm cubed is the same as 24 dm cubed. Now all we need to do is do a mole ratio. So we know the number of moles of zinc, and so because it's a 1:1 ratio between zinc and hydrogen, I'm going to use that. So zinc to hydrogen is 1:1. So we said that zinc was 0,018. That means hydrogen will be the same. Now we can calculate the volume by saying number of moles times Vm. Number of moles 0,018 multiplied by 24, and that's going to equal 0,4296 dm cubed. Question number 8. A solution of iron 2 nitrate reacts with aluminium according to the following unbalanced ionic equation. Question 8.1.1. Define the term redox reaction. So a redox reaction is a reaction in which electrons are transferred. Question 8.1.2. Identify the reducing agent in the above reaction. So the reducing agent is the substance that was oxidized. So oxidation, remember, oil rig. Oxidation is loss. So we're looking for the thing that lost electrons. So aluminium went from 0 to 3 plus. Fe2 plus went to Fe0. So aluminium is the thing that lost electrons. It became more positive. So Al is our reducing agent. Question 8.1.3. Give a reason why the nitrate ion is a spectator ion in the reaction. And it's a spectator ion because its oxidation numbers do not change. So the oxidation numbers of the nitrate ion stay the same. Question 8.1.4. Give a reason why the reaction is unbalanced. It's unbalanced because the overall charges are not the same. And what I mean by that is, if you divide this into two, so you have your left-hand side and your right-hand side, your left-hand side has an overall charge of 0 and then 2 plus. So 0 plus 2 is 2. So the overall charge on the left is 2 plus. Whereas on the right-hand side, the overall charge is 3 plus. And so because of that, it's not balanced. Moving on, question 8.2. The incomplete ionic reaction between dichromate ions and tin 2 ions, SN2+, in an acidic medium is given below. Question 8.2.1. Write down the oxidation number of Cr in Cr2O7 2-. So Cr2O7 2-. So the oxygen we start with, oxygen has an oxidation number of 2- because there's 7 of them. That's going to be minus 14. Now, if the overall needs to be minus 2, that means this needs to be plus 12. And because there's 2 of them, each one must be plus 6. So the oxidation number of Cr is going to be plus 6. Moving on, question 8.2.2. Write down the reduction half reaction. So reduction is gain. We're looking for whatever has gained electrons here. So Cr went from plus 6 to plus 3. So Cr underwent reduction. It gained electrons. So we're going to look for that half reaction in our table 4b. Now we will have to look here. Let's go down. Here we go. Okay, so remember that oxidation is written from right to left. Reduction is written from left to right. So we're going to write down Cr2O7 2- plus 14H plus 6 electrons. And that's giving us, we use a single arrow for a half reaction, 2Cr3 plus 7H2O. Let's look at question 8.2.3 now. Question 8.2.3 asks, use the table of standard reduction potentials, write down the balanced net ionic equation. So we've got the dichromate, now we've got to deal with the tin. So because tin is going to be oxidized, we're going to find that reaction above. So we're looking for tin 2 plus. Here's the tin 2 plus reaction. And as I said before, we're going to write that from right to left. So the oxidation half is going to be SN2 plus going to SN4 plus 2 electrons. Then the reduction is going to be Cr2O7 2- plus 14H plus 6 electrons going to 2Cr3 plus 7H2O. Now we need to balance the electrons. I'm going to multiply the first reaction by 3. So this is going to become 3 here, that's going to become 3, and then that's going to become 6. Now that the electrons are balanced, I can now bring everything down. So the electrons will cancel here, and the electrons will cancel here. That means my overall is going to be 3 SN2 plus Cr2O7 2- plus 14H plus, giving me 2Cr3 plus 7H2O plus 3SN4 plus. And that's the whole paper. Guys, if you stuck around till the end, Please leave a like, share this video with others, and don't forget to subscribe for more. I'll see you in the next one.